Hi, everybody. Welcome to this crash course in binomial probability. All right, we will talk about binomial criteria, and often we will talk about a binomial setting. This arises when we perform n independent trials of the same chance process and count the number of times that a particular outcome, which we usually call a success, occurs. All right, we have these four conditions that need to be met for a random variable to be considered a binomial random variable or a binomial setting to occur. First, binary. There needs to be two possible outcomes, and usually we refer to those as success or failure. The trials have to be independent of each other. That is, knowing the outcome of one trial must not tell us anything about the outcome of any other trial. We need to have a set number of trials. We refer to these number of trials as n, and this is fixed in advance. And the same probability of success for each trial, we refer to the probability of success as P. A quick and easy way to remember that is to check your bins. See this mnemonic device right here. Binary, independent, number, same probability, right? Bins, great. So for example, let's determine whether these are binomial settings. A, roll a fair die 10 times and let x equal the number of sixes. Well, it's binary because there are success and failure, a 6 or not a 6. Independent, yes, knowing the outcome of past rolls tells you nothing about the future of other rolls. Say a set number, yes, there's n equals 10 trials. Same probability, yes, the probability of success is always 1/6. This is a binomial setting. The second one, B, shoot a basket 20 times from various distances on the court and let y equal the number of shots. Well, in this case, we do have the binary, we do have the independent, we do have the set number of trials, but we do not have the same probability of success because if you can imagine shooting baskets, your probability of making a shot changes depending on the location that you are in the court. So it is not a binomial random variable. This last one right here, observe the next 100 cars that go by and let C equal the color of each car. That sounds kind of crazy, and you can see that no, it's not binary because there are more than two possible car colors, and the same probability of success. No, because uh, a success hasn't been defined, so we can't even determine the probability of success. And this is not only a binomial random variable, it's not even a random variable. So a binomial random variable specifically is the count of successes x in a binomial setting. The possible values of x are 0, 1, 2, all the way up to the n number of trials. So if you can imagine flipping a coin 5 times and a success is the number of heads, you could have 0 or 1 or 2 or 3 or 4 or 5 heads. The probability of distribution of x is a binomial distribution. And here's the binomial probability formula. It uses some combinatorics right here. This is said n choose k. This is the formula using some factorial. You can also do this very easily on your calculator. So k is the number of successes, n is the number of trials, p is the probability of success. So let's see how to apply this right here. So 3 4-sided dice are rolled. Let x equal the number of ones that are observed after a roll of three dice. Find the probability of rolling exactly 2 ones by using the formula. So here's the formula I just showed you. Plugging in the values, we would get this. And this is what you would want to plug in on your paper, or write on your paper, I guess. We have 3 trials, talking about 2 successes. A success has a probability of 0.25 because it's a 4-sided die. We have a 0.25 probability of rolling a 1. 2 is the number of successes. 0.75 is the probability of not rolling a 1, since there are 3 sides that are not a 1. And we're talking about 1 failure. And that comes out to be 0.141. And then let me show you how I got that. All right, I would write this on my paper, and then I would go to my TI, and I would go second distribution, I would scroll down to binomial PDF, that's option A, and I would enter 3 trials. P is 0.25, X value is the number of successes, which is 2. I would paste that in, and I would get 0.141. All right, moving on. If you wanted to see more of a tutorial on how to do binomial calcs on your TI, go to the slideshow, which is embedded in Canvas, and you can click on these and watch more. All right, so for our free response question binomial calcs, these are the things we need to do. We need to state the distribution and the values of interest, specify a binomial distribution with the number of trials n and success probability p, and the value of the variables clearly identify. Step 2, we want to perform some calculations. We need to show some work. We got to do one of the following. Use the binomial probability formula to find the desired probability, or use binomial PDF or binomial CDF and label each of the inputs. Be sure to answer the questions that was asked. All right, so for example, when rolling two fair six-sided dice, getting a pair of ones is called snake eyes. The probability of getting snake eyes on any roll is 136. Suppose that a game player rolls the 2 dice 80 times. What's the probability that the player gets exactly 2 snake eyes? Interpret the value in context. Well, here is our solution. Let x equal the number of rolls that result in snake eyes. X is a binomial random variable with n equals 80 and p equals 136. All right, so we plug into the binomial probability formula, and we would get 0.27089. So we would interpret in context. There's about a 27% probability that exactly 2 of the 80 rolls of the dice we result in snake eyes. Right, so we defined our random variable. We defined n, the number of trials, and p, the probability of success. We plugged into the formula, and I used my TI to get this number, and then we interpret in context. All right, so using your TI, you would have binomial PDF again. Remember, that's second distribution, 80 trials, probability of success, exactly 2 snake eyes, and paste it, and we get that number. All right, here's a cumulative binomial calc. So this is binomial CDF. Should the player be surprised if fewer than 2 of the rolls result in snake eyes, calculate an appropriate probability to support your answer. So I want to know the probability that 2 or less, that's the probability of 0 or 1. Right, so let's go back and let's define x as the number of rolls that result in snake eyes. X has a binomial distribution with n equals 80 and p equals 136, right? We want to define a random variable and assign values to n and p. So we could plug this into the binomial probability formula, but it's a lot to do. You end up getting 0.3345, and there's a much easier way than doing this on your calculator. But we would answer in context by saying, because there's about a 34.5% probability of getting fewer than 2 snake eyes and 80 rolls, the player should not be surprised if this happens. All right, so to get this value on your calculator, you would go to second distribution again, and then binomial CDF. C stands for cumulative. That's option B on your calculator. Again, 80 trials. P, the probability of success is 136, and X is going to be 1 because that's 1 or less successes. All right, so this could be the probability of 0 plus 1 success, and we get that answer that we got on the last slide. All right, we might want to describe a binomial distribution. Mrs. Patanud asked each student in her AP statistics class to toss a coin and record the result. There were 28 students in the class. Assume that all the coins are fair. Let x equal the number of coins that landed heads. Here's a histogram of the probability distribution of x. What probability distribution does x have? Justify your answer. And describe the shape of the probability distribution. Well, for part A, it's binary because there's success is 5, failure is tails. Independent, knowing the result of one student's coin does not help us predict the result of another student's uh, there is a set number of trials, n equals 28, the same probability of success, which is 1/2. X has a binomial distribution with n equal 28 and p equals 1/2. And for part B, the probability distribution of X is symmetric with a single peak at X equals 14. All right, the mean and standard deviation of a binomial random variable, they're very, very easy to calculate, much easier than we did in the previous sections. Uh, the mean, or the expected value, is just n times p. That's all you got to do. Super, super easy. The standard deviation is the square root of n times p times 1 minus p. Again, very, very easy, much easier than we did with just any random variable that we did in the last sections. All right, so let's find the mean and the standard deviation and interpret in context. Again, there's 28 students that are going to flip a coin. X is the number of coins that land heads. And so the mean is going to be n times p. So that's 28 times 1/2. That's 14. If the coin tosses were repeated many times with groups of 28 students, the average number of students in the class who get heads would be about 14. The standard deviation, we're going to calculate it by plugging in 28 times 1/2 times 1/2, and that's 2.65. If the coin tosses were repeated many times with groups of 28 students, the number of students in the class who get heads would typically vary about 2.65 from the mean of 14. And that is all I have for you. Thanks for watching this long video, and I'll see you next time.